Okay. Now, with this in mind, that this is kind of our, new and improved, the actual original Newton's second law. So with our Newton's second law, written as the average net force is the change in momentum over the change in time, then what we can find is that since we're going to work with an average net force, then what we can do is we can, that would be true. Meteors would be a good one. They burn up in the atmosphere as they, head to the surface. And once again, that would be a little tough for us to handle because of the changing acceleration due to gravity, because then they're definitely going to move more than like the 1,000 meters above the surface kind of thing. So, but yeah, but that would be a nice example as well. Definitely. But if we're going to work where we're doing average net forces, then we can consider forces that are not constant. Okay. Such as the forces that are involved in a collision. Okay. And so if we try to look at, collisions, like when the ball hits the table type of thing, then the ball is going to come down and contact the table, and then it's going to create a compression on the ball, and then it's going to uncompress and rebound back up off the table. And so then our force goes from little to big to little. And so the force between the ball and the table is definitely not constant. Okay. And so while I don't explicitly know how that force will behave, we have that general idea that when you look at the deformation on the ball and it goes from just touching to deformed to untouching, then when we go in and we look at our, magnitude of the force versus time kind of idea, then in some way it's going to go from little to big to little, something like this. So it could be symmetric, it might not be symmetric, but we'll go with this kind of Gaussian or bell curve style shape to the graph like so. And so from here, then what we can see is that from this point to this point, this is the amount of time for the collision. So this is the time interval. So this is our collision time. And we can go in and look at this value here. So then that's the maximum amount of force exerted between like the ball and the table in the collision. And then when we handle these kind of non-constant forces, then this is going to be done in a way kind of just like we did on the trip to Dallas, back in chapter 2. Okay. And so then what we would do is we'd look at this interval over which the force acts. And if we're going to work with an average value, then it's just like what we had talked about before, is that we want to go in and figure out where would we cut the graph so that the area above the cut line would fill in any gaps or holes below the cut line. And wherever we find that cut line, then that's where our average value would sit. And so what that would do is that would go in and change from this funny shaped bump into this rectangular structure. Okay, where this height would be this is the average force, and then this width would be the time interval over the collision, so the collision time. Okay, and then by construction, what we get is that this funny bump and this rectangle is that these should have the same amount of area. And the thing is that when it's a rectangle, we know it's, length times width is the amount of area. But when we have a funny bump that I don't even know what the function is, then I can't tell you what the area is, but they're the same. Okay. And so this gives us some way to calculate that amount of area. And so that would be our average force times the time. And then what they'll do is they'll go in and they define this to be a quantity that they refer to as the impulse. Okay. And so what we actually will want to work with is not just this amount of area, but we want to define what they refer to as the impulse vector. And so that'll be our vector J. And sometimes they do a vector I for impulse instead of J. And then what you get is that this is going to be our average force times the amount of time. And so just like we did with the definition for work, then what they'll do is they'll go in and they'll track this by type. So for each type of force, where they'll put a little subscript on here, like we always did, then you get the applied force, the normal force, the gravitational force kind of things. And so each one of those will have an amount of impulse associated with them. So the applied force will have an impulse amount, the normal force will have an impulse amount, the gravitational force will have an impulse amount type of idea. Okay. And what we can think about is that this is kind of another way to measure essentially the effectiveness of a force. Okay. And I always picture that this is essentially very similar to what we did with work. So work was the amount of force acting over the distance or over the displacement, such that the force was, the component of the force that assisted the motion, or could be resisting the motion and doing negative work. But if it was perpendicular, then it didn't count in the calculation for work. And what we have in this instance is you're going to take the force times how long it was acting on the object in order to produce some sort of, change in the motion of the object. And so then, very similar to what we would do is we would calculate the impulse due to each type of force, just like we did with work. And then what we would do is we would go in and, add these all up. And what we would get is what they'll refer to as the net impulse. Okay. And they could either do the sigma sign for the impulse or just write a net subscript. And so then this will be just like we saw with the work, will be our average net force times our time, like so. And then if we go in and, look at our Newton's second law, then we had that average net force, which we could rewrite just like this. So summing the forces and then taking the average, or the net force and then taking the average, that's really the same thing. And if we go in and multiply this time over to the other side, then what we get is the change in momentum. Okay. And then this expression, this is referred to as the impulse momentum theorem. Okay. And I had this idea that it's, very similar to what we got with the work energy theorem. So with our work energy theorem, we had that the net work was our magnitude of the net force times the magnitude of the displacement times the cosine of the angle between the two when we place them tail to tail, gave us the change in kinetic energy of the object. So by having a net amount of work done created by our net force, then we can get a change in the kinetic energy, change in the motion, and having an average net force acting for some amount of time gives you a net impulse acting on the object, which causes a change in the momentum. So again, a change in the motion of an object. One of the big differences between these two is that this expression is a vector expression, and then this one is a scalar. So this one's a scalar, that one's a vector. And in fact, having taken chapter 7, where we pretty much only worked with scalar quantities, and we did not really, in any dramatic way, didn't really work with a lot of vector quantities, then we're gonna make mistakes when we come back to the vectors. That's how it always goes. I mean, so we just gotta be aware and be careful. Because probably the most common mistakes that'll be made are that we won't work with components, or that we will forget to put signs on the quantities to indicate the directions in our coordinate system that we have to pick, versus with the scalars, we didn't have to do those things. So in some sense, this type of theorem, the work energy theorem, is a little simpler to utilize because it is a scalar equation, versus the impulse momentum theorem is a little more difficult because it's a vector expression. So finding this net impulse is a bit more difficult than finding the net work, because you have to add these by components, and whereas these were just signed numbers. So, trade-offs, one way versus the other. Okay.